Okay, good morning, everyone. I have the privilege of introducing Ashlyn Spector, so thank you everyone for joining us. So I'm going to tell you a little bit about Ashlyn before she gets started. So Ashlyn was born and raised in Tampa, in Florida, and she told me that she always wanted to be a paleontologist until she started undergraduate and found geology as a whole when she went to the University of Florida, where she majored in geology, and she got to do things with GIS, and she did research in salt marshes in Florida and Georgia, and that was before she came here to Rutgers. So that experience working in salt marshes and living in Florida gave her interest in the practical application of geology and applying it especially to coastal mitigation and coastal management. And so that is what she took when she basically created this project that she's going to present. So I'm very proud of her for coming up with this idea, for coming up with how it's going to be done. And without her motivation, this project would not happen. So I can't wait for everyone else to see these results that she did. So Ashlyn, the stage is yours. So take it away.
All right. Thank you for that introduction, Lauren. I really appreciate it. Okay. Let me just share and get into presentation mode. All right. Everyone can see my screen? All right, great. So hi, everyone. Today I'm going to discuss my thesis work that I've been completing over the past year and a half. I'm sure you've heard some talk of using drones at some point, and today I'm going to talk about that with my thesis titled Applications of UAVs, or drones, for Coastal Monitoring at Holgate, Long Beach Township, New Jersey, located on Long Beach Island. So to orient ourselves a bit throughout the talk, I've broken it up into 5 sections. And first, I'll introduce what I'm doing and why. Then I'll discuss some necessary background information, and then walk through my methodology and discuss the results. Finally, I'll wrap up with the conclusions from this study and future work. So, what am I doing? Well, in short, I have used drones to perform monthly beach monitoring at Holgate, New Jersey, to understand changes of the beach and dunes. Okay, so what? Why does this matter? Well, let me give you 5 reasons why this really matters. The first one is that there are 239 communities on the New Jersey shore, all with their unique set of beach, all with their unique set of needs, especially for management. The second reason is that coastal zones host a large percentage of the population in the United States, that's 39%. And because of this, there's also a lot of cultural, social, and economic importance due to these large communities in our coastal zones. For New Jersey specifically, even under 2 feet of coastal flooding, which is already reached from nuisance flooding and storms, you have over 35,000 people exposed, over 24,000 homes, and of course, other infrastructure like roadways, hazardous sites, and so on. Coastal areas are already facing erosion as well from flooding and the storms, which is getting worse by the effects of climate change. This graph right here, this is showing the number of current properties at risk of flooding, tidal flooding based on county, both at the current sea level and then at projected sea levels for 2050. So if we're just focusing on Ocean County, which is where our study area is located, this value from current day to 2050 sea levels is at a minimum doubling. And for the following 3 reasons alone, this is further supporting that coastal management is really important and that we need affordable and flexible monitoring protocols to better understand our coast and how they're evolving. And on top of this, To aid with this management, what we really need are frequent, accurate measurements taken of these areas that can provide us insight on what aspects of the environment are impacting topographical changes on the beach. This is to help us understand evolving coastal zones and understand how they'll impact our communities. So now that I've hopefully convinced you with these 5 overarching points why this is important, I want to dive a bit into some background information before we move forward. So of course, a little bit of geologic context. 20,000 years ago, when the Laurentide ice sheet began to retreat, the New Jersey coastline was about 150 kilometers offshore, approximately on this figure on the right, at the 200-meter isobath, the dark blue line. Then over time, as sea level was rising during the Holocene transgression, sea level was still rising, but it stabilized a bit, and the barrier islands that we know today along the Jersey Shore formed a few thousand years ago. But I would like to draw your attention to one barrier island in particular that also happens to be boxed in on this figure, and that is Long Beach Island, or locally, as I found out through living in New Jersey, referred to as LBI. And so LBI is an 18-mile long barrier island located in the southern portion of New Jersey. It's bounded by Barnegat Light Inlet to the north, the Atlantic Ocean to the east, Little Egg Inlet to the south, and then Barnegat Bay / Manahawkin Bay to the west. There's also the Forsyth National Wildlife Refuge, which occupies the southern portion of LBI and into the bay, which is national land and is undeveloped. And so overall, LBI has quite a lot of people living on it, especially seasonally, and it's composed of 6 separate municipalities. Just to give a bit of history on LBI, prior to what we know as it today as being full of vacation homes, it was relatively undeveloped and just some fishing shacks until after World War II, there was a housing boom. And then in the 1970s and 1980s, there was another boom for vacation homes and beach homes. And so today on LBI, the 19,000 houses and businesses are assessed at a minimum value of $15 billion. This is a picture on the left of LBI looking south towards Holgate in 1931, and then a view in 2018 looking north of just to get an idea of how much development there's been. And I'm talking about this even though it's like, wait, this is a geology talk. Well, this is to further emphasize all of this development means more people's livelihoods and communities are at stake, and it further emphasizes why we really need to understand what's going on with our coastal zones. And so to orient ourselves a bit more with what is affecting, of course, Long Beach Island, New Jersey coast as a whole, and also most of the globe, there's sea level rise occurring. New Jersey in particular is feeling these effects a little more than the global average. And that is also because of the glacial isostatic adjustment that's occurring, as well as there are some localized effects of sand compaction as well. But mainly that New Jersey is getting hit even harder with a greater rate of sea level rise. And on top of this, New Jersey is also experiencing already quite a number of high tide or nuisance flooding or sunny day flooding events. So for this chart representing Atlantic City, which is just south of LBI, in 2020, the likely range was 17 days of flooding a year. And by 2050, we're looking at a likely range of 120 days. And so to zoom in a little further, because obviously I did not study the entire 18-mile island, We're zoning in on Holgate in particular, which is part of Long Beach Township. It is a 1 mile stretch of beach on the southernmost portion of the island. It is the last bit of developed area right before the wildlife refuge starts. And so how did I settle on Holgate? Why did I pick this area? Through the C2R2 program, Coastal Climate Risk and Resilience program, I had to take a summer course where we virtually this year met with different municipalities and townships throughout the state. I had actually spoken with the sustainability director for Long Beach Township, Angela Anderson, and she was talking about how Holgate in particular has been really facing erosion issues on their beach, and residents are not sure why this is happening, despite them constantly renourishing and dumping sediment onto the beach. And so when I was trying to think of a project, I thought back to this. It was like, this seems great. I can both, explore the science, but I can also go ahead and, have a practical component to this. And so, of course, there are other reasons why to look at Holgate. And one of them is the fact of the amount of coastal management and risk management that has occurred. So this figure on the left is showing the U.S. Army Corps of Engineers. This is a huge coastal storm risk management project that they've had ongoing throughout the shore, including the entirety of LBI, getting renourishment from offshore sand. But on the municipal level, Holgate is also doing some both hard and soft engineering structures to help mitigate from storm and flood and just general erosion. On the top figure here, these both were taken with the drone. These are actually bulldozing tracks along the beach. We've noticed pre and post storm, they bring a bulldozer out to push sand from the lower part of the berm up to the toe of the dunes to help reinforce them. And then as of 2019, they've also constructed a brand new terminal steel groin to help trap sediment that is drifting south to help build out the beach in southern Holgate. So another really interesting and compelling part of Holgate is that it sits right on the border of an undeveloped portion of the island. And so this is the wildlife refuge I've been talking about. This is a USGS little GIF of the island changing through time. And so you can see that it is moving and sediment is building lengthwise, but it's also rolling back towards the mainland, which is showing naturally how the island wants to progress, but then how the developed portions, which are heavily fortified by human infrastructure, are unable to move. And so a final reason to specifically look at Holgate is just how much it has been affected by storms over time and continues to be greatly affected. These are just a few examples of storms that have really eroded the beaches and have also fully broken through and breached the island. And so one of those famous ones is the Ash Wednesday storm of 1962. This is the picture in the top right corner showing at Harvey Cedars, which is north of Holgate on LBI. Of course, Superstorm Sandy in 2012, and this is a picture of homes along Holgate. And then there's also smaller hurricanes and nor'easters that still have catastrophic effects, such as these two pictures from Hurricane Michael in 2018, which is also showing at Holgate. And so all of these things, of course, need to be understood. The effects that storms and flooding have on the area. And so that's why there are coastal monitoring programs in place to help with management. Some of these key players in the state of New Jersey include the U.S. Army Corps of Engineers, the New Jersey Department of Environmental Protection, Stockton University, and the National Park Service. However, there are some limitations to these groups, even though they do great monitoring work. One is that some of these only cover very specific areas. The National Park Service is, of course, covering their land. DEP and Army Corps, yes, they can work throughout the whole state, but they're typically on very specific projects that they have large amounts of funding for. And And Stockton University, I will note, they do perform, and they have been performing biannual beach monitoring for over 30 years. However, they're looking at 1 mile intervals along the shore. They're measuring 2 times a year, and they're using traditional survey methods. So this is more of a long-term data set that's a little more sparse and doesn't really center in on the scale that we're trying to look at in this study. And so that leads to one of the other limitations, that none of these capture really shorter events with a high accuracy data set, a high resolution data set. And so that's where drones come in. So you've probably seen them referred to also as UAVs, as such in my title, or unmanned aerial vehicles. They are the same thing. And drones are really useful besides just looking really cool and being fun to use. One of the first things that's really important is accuracy. They're able to provide highly accurate data sets. In the ideal conditions, you're able to get centimeter scale accuracy, vertical accuracy from imagery that it collects, as well as any other sensors you want to add on. They're relatively affordable as well. Now drones can start in the upper hundreds, but then sky's the limit for how much money and cool things you want to put on it. But overall, this is much more affordable than purchasing a traditional LiDAR set and then chartering or hiring a plane to go fly it across your study area. They're also pretty easy to use, and the learning curve is not too difficult. The really nice thing about these is there's a lot of applications for your phone or other devices where you can put in your flight path, hit go, and the drone will just take off. Another really important and useful part of drones is the accessibility factor. Drones obviously can access places that you can't access by foot. They also cover large amounts of area relatively quickly. So it saves a lot of time for data collection. And then, of course, as I mentioned a little earlier, you get a variety of data depending on all the different sensors and equipment you want to load onto your drone. But even just sticking with the traditional camera and imagery collection, you get a lot of information from this, including elevation data and location data, all from the metadata of the images. And so when we combine this with a very specific photogrammetry technique referred to as structure for motion, we get this really powerful combination. And so structure for motion, we can get super into the weeds from this, but to keep it very simple, looking at this figure here, essentially what this is you capture different pictures of a specified scene or object. So all these images taken at different angles. And then by putting this into a specific program of software to process structure for motion technique, it's able to identify similar features throughout all of the different photos and space them together to make a 3D model from 2D imagery. So obviously that factor alone is really great for being able to understand the 3D component of from 2D imagery. However, to make it even better, we can also georeference this data and make it so we can analyze spatial changes and make measurements from this. And so the accuracy of these spatial changes are obviously going to be based on how accurate our georeferencing system is. And so in this study, we use a RTK GNSS system, so a real-time kinematic global navigation satellite system. Essentially, it's just a much more accurate form of GPS. And RTKs can achieve 3 to 8 centimeter vertical accuracy compared to 15 to 25 centimeter vertical accuracy for LiDAR in coastal environments. So it's definitely even an upgrade from really expensive LiDAR systems. And so when we combine the drones with the RTK and structure for motion, we're able to create this powerful new methodology that allows us to cover great amounts of area in a relatively quick amount of time without sacrificing the high resolution of our data. And so shifting into methodology, I just want to walk through how much data we collected. And so we did 8 monthly surveys from October 2020 to May 2021. And we collected drone imagery. So this figure on the right is showing the total area, which is 3 of the colored zones. And each of these colored zones just represents a flight path, since our batteries only had about 25 minutes of flight time. We also collected the RTK ground control points. These are what georeference our model. And then we also collected beach profiles with the RTK, which are shown in this figure on the left here. So transect 1, 2, 3, 4, and 5 throughout the whole study area. And so we were ideally hoping to fly when it was low tide to get greater exposure of the dry beach. And when there's no wind or precipitation, that way the flight can go smoothly. And then of course, either later in the day or earlier in the day to reduce shadows that could distort resolution of our imagery. And so here are just pictures of what our ground control points look like. And these were placed throughout the beach, both close to the water, in the middle of the beach, and up by the dunes. And so from after collecting our field data, we put all of this imagery into Agisoft Metashape, which is a structure for motion program. And this is, of course, not our study area since it is a volcano, but it gives a good example of the workflow that we completed. So just to go through this really briefly, we uploaded the images into Agisoft and then aligned them. And what this alignment does is create a sparse cloud, which is essentially all of the images trying to identify overlapping features and place them where they think they belong in a 3D model. Then we input our ground control points coordinates from the RTK and re-optimize to create a dense cloud, which is the program taking these features where they thought they were and applying actual spatial data to this. That way, each of the points that we see in this model actually has a location tied to it. Then we created a mesh, which is just to give it some texture, and then have our 2 outputs, which are a digital elevation model, or DEM, and an orthomosaic. Here's what these 2 outputs look like. Digital elevation model seems self-explanatory, but it gives us the elevation of the study area. And the orthomosaic is simply all of the photos that we took from the drone stitched together. That way we can see the area as a whole. So we both get a lot of really good qualitative and quantitative data from this. And so the next step is utilizing some volume change calculations. So we used a volume change script modified from Sudi et al. 2017. This is a National Park Service protocol that utilizes RTKs to understand volumetric change. But we modified it a bit by using our digital elevation models derived from drone and RTK data. And essentially, the gist of this calculation is that we take our digital elevation models created from the survey data collected at different times, and we calculate the volumetric change that occurred within that time span by calculating the average difference between the elevation values for each of these grid cells within the 2 DEMs, and then multiplying that by the topographical area covered by the grid cells. Okay, and so we have all this great data of how the beach has changed in terms of volume, but we also want to connect that to factors in the environment. So one of the first ones that seemed pretty obvious to do, especially with the availability of data, is looking at water levels from a nearby tide gauge in Atlantic City. So this is hourly wave data or tide data plotted over the course of the study from October to May. And so these little red symbols are our drone survey dates. And then there's also, I've marked peaks of named storms as named by some DEP coastal monitoring reports. So you can see there were quite a few that we were able to capture the before and after of. And so this slide is going to act as a bit of a transition between the end of methodology and starting to analyze results. And there is a lot on here, but I'm going to walk you through what these panels are showing, and then we can talk about what they mean. So this top panel, A, is simply the water levels. Instead of hourly, since that would be a lot of data to plot, we average them out a bit. And this is plotted over the course of the survey with these dotted lines indicating our survey dates. And we have this red line along the top, which is representative of the 97.5th percentile, in which any water level that is hitting this line or above is indicative of a storm event occurring. So this second panel here in the middle with the light blue line and the dark blue line, these are correlated with the water levels that we're observing in panel A. And so I just want us to pay attention to the light blue line for now. And what this is this light blue line correlates with the average water level between the first survey date, which is October 17th, and any given point in time. So anywhere else along this survey. So essentially, if the slope is positive, the average water level between these 2 points, so the beginning of the survey at any point in time, is greater than the average water level over the course of the entire survey. And so this dark blue line is simply doing the same thing. Instead of comparing it to the entire average of the full survey, it's looking at an average of every 30 days. This line and the interpretation of it, this is being worked out a little more for some future analysis. So really, we're just going to talk about the light blue line a little further, but essentially they're showing the same mechanism. And so this bottom panel here is showing the volume change for each of the survey dates relative to the baseline of our first survey of October 2020. And so this is divided into 4 different symbols. This black circle is representing the survey, the entire survey as a whole. So I put in a little orthomosaic of the area just so you can get an idea of what we're looking at, this 1 mile stretch. And then we've also calculated the south, central, and northern compartments, what their volume change was. And so if you line up the colors, I've put them where these cutoffs are for compartment analysis. And you can see the northern section, central, and southern. So to get into a bit of the results here, when we look back at this middle panel, what we're looking at is that these higher values in the light blue line are indicating a greater impact of storminess on the beach. So these higher elevated water levels. And this overall positive slope is indicating a period of storminess that's occurring. And then the opposite is true for the negative slope, which is indicating a period of quiescence where there's not as many storms and the beach has some time to recover. Well, we can see a direct correlation between this and the volume changes on the beach. So when we look down here, we see this general trend of the volume going down until we hit this February survey date, and then they start to go up again. Well, this correlates right to the maximum point where we have this inflection from a positive slope to a negative slope. And so we have the overall average that goes down and does accumulate some sediment towards the end of the survey. However, it does not accumulate enough that it's fully recovered. And in fact, even when we're looking at this, when we start to look at the different sections taken out, the northern section is really making up for the average and raising that a bit for the entire area. The south and central areas overall are losing a lot more sediment and are not able to gain as much back compared to the northern section. So there's a difference between these 3 parts of the beach. just to better visualize that, this is demonstrating the volumetric change, kind of using a heat map feature. And this middle panel right here is from the beginning of our study in October to the end of May 2021. This left panel is showing October to February, representing the time of storminess. We had 7 storms occurring. And then this panel on the far right is showing February to May, our period of quiescence, where we only had 2 storms. And I know these values, or these font is a little small, but essentially I hope you all can see that it's a dark green, which is representative of a meter or greater of accumulation. And then when we look at the period where there's a lot of storms, we see this period, a lot of this dark red color, which is also indicative of greater than a meter change, indicating loss. And so when we combine these, we can see over the course of the study, primary loss in the central and southern compartments. The compartment borders are these little dotted lines. And really the only green is up in the northern section. And so we also have our RTK breach profiles, which serve a few purposes. One of them, of course, is it's just more data that we can get. It also ground truths the model data that we're seeing, as well as the drone information, since RTK is the most accurate component that we're working with. And so I just want to point out a few things here. So we have profiles 1, 2, 3, 4, and 5, 1 at the northernmost section and 5 at the southernmost section. So just looking at this as a whole, you can see that profiles 1 and 2 are nearly double the length or the width of profiles 3, 4, and 5. And this is just showing the variability of the beach, even within this 1-mile section of Holgate. And so just to point out a few things, in profile 1, this red line where the berm is at the greatest height and area is at the beginning of our survey. And over time, it gets eroded back, but then starts to build back in February, but not quite reaching its original position as it was at the beginning of our survey in October. Another really interesting thing is that in these northernmost profiles, the majority of the changes are not really occurring up by the dunes or in the dunes. It's mainly by the lower portion of the berm and into the step down into the swash zone. And then when we look at moving down to the southern areas, profiles 4 and 5 start to get more affected and change up through the dunes and not just the lower portion of the berm. And in fact, for profile 4 especially, which is right by the Pershing Avenue jetty, this was especially hard hit over multiple surveys where a large and steep dune scarp and cliff was eroded out. And you can actually, these are some pictures from that February survey to see what these effects look like. So you can see just how dramatic this was, particularly in the southern and central portions of Holgate. And this upper right picture is just showing some more of the bulldozing tracks that the municipality tries to do. And here's another just visual example. This is showing the Pershing Avenue jetty, like I just mentioned, around this area. There's quite a bit of erosion. And so this was taken February 17th, 15 days after nor'easter Elena, where you can see a lot of these wood pilings from the old jetty exposed. And then in March, later on, they're no longer exposed, whether that's from just natural movement of the waves and sand in the environment, or maybe from the bulldozing. But overall, just want to show a little bit of the quantitative side, where this is further just showing the actual values for a mean volumetric change for the monthly surveys on top here, and then for total surveys that span from beginning to end and during the stormy period and during the quiet period. So really I've just color coded it where red is indicating loss, and the blue color is indicating volume gain. And so you can see right here, it's majority red until we reach the January to February period, which is again our inflection point between the sediment loss and then gain, primarily until May. And then this is seen also through beginning of end to the survey, where the south and central portions are losing about the same amount of sediment per compartment, and the northern area is gaining, while all of them are losing sediment during the stormy period, October to February, and then all of them are able to gain some sediment back from February to May. And if you're wondering why these values may not add up to these, that's just because these values are the mean volumetric change for each of the individual compartments. So if you multiply these just by 25, then they all add up to this. So that was a lot of stuff and a lot of information. We got so much data during this study, but I settled on 4 key takeaways that I think are really important from this. One is that we are able to modify an existing monitoring protocol that uses RTK and integrate this successfully with drone technology. And the RTK combined with drones and structure for motion are a really powerful combo, both in terms of accuracy, so providing us really high resolution data, and time. It saves us a lot of time rather than going out and collecting back-to-back RTK surveys where we can spread those out a bit more, combine with the drone information to fill in those gaps, and still get really great quality data. Also learn that volume change is tied to storminess, as indicated by the beginning of the survey in October to February, and that sections of the beach are experiencing different levels of erosion and accumulation, as witnessed by the south and central portions, overall losing a lot of sediment compared to the northern section of Holgate. And so there is a lot of future work to be done. We are incorporating wave and longshore drift data on top of this, since there are obviously other environmental changes we need to look at. It's important to collect summertime data. This was not originally done due to drone ordinances and all the tourists on the beach from the town. But we're hopeful that we could collect this in the future. That way we can better understand where sediment is moving, if it's being lost or if it's just moving offshore in the system. And of course, multi-year surveys would be really useful for just having a larger data set. And then right now, we're also working on publishing our current results. And so just wanted to give some acknowledgement to all the wonderful people in my life. A huge thank you to my advisor, Lauren. I couldn't have done any of this without you. You've been a really incredible mentor and have guided me through so much. Another incredible mentor and peer is John Schmeltz. Has been wonderful to collaborate and work with you and learn so much from you on this project and share our love of coastal geology. Of course, thank you so much to my wonderful and wise committee, Ken and Bob as well. I really appreciate all of the insight, even with this new kind of realm of using drones. And thanks so much to the supportive C2R2 family, Jean, Lisa, Carrie, Marjorie, and my whole cohort. C2R2 has been a really large portion of my grad school experience, and it's really helped me understand what I want to do with my career leaving graduate school. Of course, my fellow EPS grad students, I'm glad we've been there to support each other over this time, especially being really hard with everything mainly virtual. And of course, my family and friends for their unconditional support from Florida, Texas, wherever they're all located. I've felt it here in New Jersey. And with that, I want to say thank you so much for listening for so long. I really appreciate it, and I'm happy to take any questions.
Great job, Ashlyn. Thank you. So yes, we will take questions from the audience before we move to committee.
Should I stop sharing my screen or leave it up?
You can stop sharing your screen.
Okay.
Lauren, I have a question. It's Rick.
Go ahead, Rick.
Hey, Ashlyn, great presentation. So much there. Are you able to contact the local municipalities, the DPWs, get logs of when they actually did bulldozing during your survey, so you can tease out what might be man-made recovery and what might be natural?
I have really wanted to do that. I actually sent out multiple emails to some people in the upper levels of the municipality for Long Beach Township, and they're like, "Oh, we have no idea," or "We don't know where those would be kept. Contact the police station." And I kind of got a bit of a runaround. So it would be excellent if I could track down where they have logs. I'm sure there's some, like, they have to sign out when they're using
Sure.
the equipment. Because that is something I was also very interested in uncovering is, okay, what if we can place a timeline of renourishment events from the state and also have the timeline of when there's more localized mitigation going on, especially for the bulldozing. So that's a really great point. I would love to have access to that data.
I would think you would be able to get it somehow.
Yeah, I think I just got to find the right person who's like,
Right.
"Oh yeah, I know where that's at," and can help me.
Great. Okay. Thank you.
Ashlyn, there's a question, couple questions in the talks. I'm sorry, in the chat. Parth asked, in the beginning, you mentioned coastal areas and 39% population. What distance defines the coastal areas, within 5 to 10 miles or some other distance?
I just expanded the chat instead of lowering it instead. Let me see if they cite what they use, since the statistic was taken from Climate Central, and I don't want to give an inaccurate value. Let me see. I don't see a value they use on here, but that is a good point that I should see explicitly how they're defining coastal area, and what they're actually giving this for what value they're using. If it is something pretty small, I would imagine it would be at least 5 miles if I had to guess, though. But yeah, I can't say specifically what it is.
Okay, there's another question from Bari. Are there more jetties in the southern section? And in your opinion, how effective are these jetties in preventing beach erosions during your project?
Yeah, so actually, the jetties that are along the Holgate section are pretty much only in the southern portion. These are going from the parking lot at the very border of Holgate all the way to about, let me see if maybe I can pull it up. Just the beginning of the central section, there's 5 of them total. They're nowhere in the northern section. Now, I don't know historically if there are old, like, wooden ones buried, but they're all in the southern section, and how effective they are. I mean, I've seen pictures of the area right after it was renourished in 2016 of Holgate, and the beach was, I mean, enormous for how wide it was compared to what I've seen recently. And obviously, most of that has gone away for one reason or another, mainly from, I'm sure, storm events, and just over time, the area is losing sediment. So I don't know. I have to imagine they're having obviously some effect. I just don't know if it's enough to counteract just how much natural loss is occurring.
Are there other questions? Feel free to put them in the chat or unmute yourself. Anyone else? Okay, well, if that is it, I thank everyone for coming, and be sure to wish Ashlyn luck as she moves to DC tomorrow for her NOUS fellowship that she received, which is very prestigious. We can't wait to see all the amazing things she does in the legislative branch, correct, Ashlyn?
Yes.
Yeah, so she gets to apply some of this practical knowledge that she gained to actual policy. So we all wish her luck and can't wait to hear about the great things she does. So, and she's moving tomorrow, so there's no no break in this. So thank
No.
you for everyone for coming, and great job, Ashlyn.